All right, guys, last lecture of the semester is today. We've got a pretty exciting class today. It's on a topic called dynamic programming. Dynamic programming is a junior level algorithms topic. I like to kind of teach kind of the more important junior level stuff at the end of 41. Last time we did graph theory. Today we're doing dynamic programming. So what dynamic programming means is using a table to write down information. Why would we do that? Because a lot of times when we solve a bigger problem, the bigger problem involves recursively solving smaller problems. And if you have to recursively solve those smaller problems multiple times, then if you can write it down, you don't have to repeat the work. Okay, that's the idea in a nutshell. So let me show you an example of what I mean by that. So if we do our basic Fibonacci, still need to redo that macro. If we do our basic Fibonacci recursive algorithm, it's going to look something like this, right? Fibber x, if x is less than or equal to 1, return 1. Otherwise, return fibber of x minus 1 plus fibber of x minus 2. And so if we see out fibber of 5, it should return 8, right? Because the Fibonacci sequence is 1, 1, 2, 3, 5, 8. So index 0, index 1, index 2, index 3, index 4, index 5. So that should give us 8. And we get 8. Cool. The trouble with this algorithm is that this is a order 2 to the n algorithm. Okay. The reason being, every time you call Fibonacci with one number higher, it calls itself twice as often, right? So the Fibonacci of 5 calls Fibonacci of 4 and 3. Fibonacci of 6 calls Fibonacci of 5 and 4. And then that 5 calls 4 and 3. And then that 4 calls 3 and 2. And then that 4 calls 3 and 2. And that 3. And it doubles basically in size every time you go up one number. So this is an extremely inefficient algorithm. This is a terrible algorithm. It's great for demonstrating recursion. There's only like 2 functions that people ever use to demonstrate recursion. It's factorial and Fibonacci for whatever reason, but it's terrible. This is really a bad garbage tier algorithm. And so we can turn it from order 2 to the n to order n by using dynamic programming. So we're going to change this into an order n algorithm using dynamic programming. And so what we do you guys understand why this is order 2 to the n? Like, order, like fibber, I'll just say f. F of 10 calls f of 9 plus f of 8, right? You guys understand this? And then f of 9 calls f of 8 plus f of 7, right? So each function call calls itself twice, and each of those calls itself twice, and each of those calls itself twice, right? You guys see this? And the thing is, like, that f8 here and this f8 here are 2 separate calls. If only it was possible to write down the answer to f of 8, and then the next time you encountered it, you wouldn't have to recompute the entire exponential thing, but you could simply make it an order n algorithm, which is what we'll do. So we'll do this. This is called memoization. Not memorization, memoization. It's like looking around here for a memo pad. Let's see here. Like a Post-it note, these things are. So, when you want to take down a memo, you write it down on the memo pad, you can like stick it on your monitor or something like that. And so that's why we call it memoization. It's like we write down the answer. Oh, the answer to f of 5 is 8. You write that down. And the next time you are asked to compute the f of 5, you're like, oh, I've got it written down. It's 8. And you don't have to do it a second time. So it vastly speeds up your code. Yeah, that is a good one. This guy here. So he splits into 2, and then each one of those Splits into 2. Yeah, that's a visualization of the Fibonacci sequence, exactly. So, yeah, that's order 2 to the n fibber. That's exactly right. So, what we're going to do is we're just going to write down the answer. So, we're going to make a static vector. Integer is named vec, because of course it's named vec. Static, again, for those of you that don't remember, it's as if I had made a global variable named vec, but instead of being accessible to everybody in my program, it's only accessible to fibber. So fibber is the only scope in which we can actually see vec, but it has global lifetime, okay? In other words, it does not get recreated every time we call the function. It does not ever get destroyed. It is a global that it has global. It's global in the sense of lifespan, but it is local in the sense of scope, if you want to put it that way. Because lifespan and scope aren't always the same thing, as we can see here. So this has, call it global, it's not exactly right, but global lifespan, but local scope. That's what static is. Okay. So now instead of calling the function immediately, it only goes out of scope when the program ends. That's correct. Yeah, that destructor is never going to get called. It's static. It is program lifespan, basically, is a better way of putting it than global lifespan. But it's, yeah, we'll do that. Right? So when the program quits is when it gets cleaned up. All right, so instead of calling these functions here, we are going to check to see if we have the answer first. All right, so the base case is fine there. We want to say if x is less than vector dot size. So if we've got the first, 10 elements computed, and we're asked for element 5, we can just return it because it's already been computed. So if x is the index, right, it's not, yeah. So we can just say we know that already. So we'll just return vector dot at like that. So if we've already asked for the size and it's complaining about signed unsigned comparison, so we'll just shut it up. No, you don't like that? Let's see here, vector dot x. I know, dude, I know. Now it's annoyed at me doing that, changing from int to size. I'm just turning off warnings right now. Okay. So yeah, so if we have the answer already, we return it. And if not, then what we're going to do is we are going to push back the answer. Vector pushback, sorry. Push back the answer, and then we will return vector.back. We could actually do all this in one line of code, but let's not be too fancy. Okay, so if we do that, we got 10. What do we do different here? What's a for loop? Girlfriend not found. Oh no. Okay. 1, 1, 2, 3, 7. Okay, what's going on here? What bug do you guys see in this code here? I can tell you what it is. It's actually not starting off the vector with the 1, 1, right? So the vector is empty. It's returning 1, but it's not actually putting 1 into the vector to start with. So we will start with 2 elements of value 1, and there we go. Now we have the Fibonacci sequence. Kind of a cool bug, right? Yeah. Yeah, it's not exactly an off by 1 issue. The thing is that the function was returning the right value, but it was never pushing the answer. It wasn't saving the answer, right? So whenever you return a value, whenever you do memoization, you should write it down. I wasn't writing down the first two, and so all of the vector elements were shifted to the left from where they should be. So yeah, that was kind of a fun bug to catch, which obviously I did deliberately for you guys to have a bit of an interact. No, it's just a mistake on my part. Okay, so that is the Fibonacci sequence, and now it's order n instead of order 2 to the n. All right, so what I'm going to do for you guys now is give you a classic job interview problem, and I want you guys streaming live, those 10 of you that have survived to the end of CSI 41, I want you guys to do a little bit of live coding for me, and I want you to solve one of the most common job interview problems, which is, you know, technically dynamic programming. And let me lay it out for you. So the notion is, and I'll even give you some starter code. And size equal read. Actually, yeah, we're using vectors. We don't need a size. We'll just use sum. Read what sum do you want to shoot for? So the user will type in something like 10. And then we'll do a while true. Vector of integers. I'm stopping here because, yeah, well, maybe you'll see in a little bit. But we're basically going to read a bunch of numbers like this, and your goal is to see which pair of numbers can add up to the sum. So if our target is 10, it's like let's say the target is 10 and the input is 8, 4, 7, 3, 6, 1, 2. The output will be 7 and 3, 4 and 6, 8 and 2. You guys see that? So you have to output all pairs of numbers within the vector or within the input. It doesn't have to be a vector. You have to output all pairs within the vector that add up to the sum. Okay? Classic job interview problem. Should take you about 2 minutes to do. I'll give you guys 15. All right? And the hint here is maybe vector is not the right, data structure necessarily, but I'm going to give it to you. I'm going to give you the starting code here as a starting point, and then that'll cut down on your lab time, so to speak. Okay, int num is equal to read. Please enter a number 0 to quit. And if we get a 0, then we break. If not, we say vector dot push back num. And that is the starting code. So let me toss this on Discord for y'all. There you go. So the code is up on Discord, and I want you guys to basically, given, the target's not hard coded as 10, obviously. That's, an input you give. And then given a bunch of numbers in a vector, you have to find all pairs. And you have to do this in order in time. Okay. You cannot do every possible combination. The max runtime of order n. All right. 15 minutes begins now. Stream your screens. You okay, girl?
Is there any possible time we can go to Barnes & Noble for after judo?
Maybe. We'll see. All right. Begin coding now. And welcome back. So, watching the stream, you guys can stop streaming now. A lot of you guys got stuck. Okay. And I saw some people trying to do like a doubly nested for loop for each number in the vector, search for all other numbers in the vector, and see if they add up to 10 or whatever the target is. There is a faster way of doing that. And the faster way of doing this is by not using vectors at all, but by using include unordered set like that. And then instead of using a vector here, we'll use an unordered set. That probably would have been faster just to type it, huh? And then instead of pushback, we will do insert. And so here's a cool thing. Let's say that we're halfway through our input here, right? And we've gone to 3. All we need to do is ask, have we seen a 7 before, right? Because the target number is 10, and we're currently reading a 3. So if 7's already been seen before, then we can just output 7 and 3 and be done. Right? So unordered set is order 1 lookup, order 1 insert search delete. And we're doing n of them, so this is an order n algorithm. And so, okay, fine, let's put vector back. Just to shush it for this gap here. Okay, so what we're gonna do is we will say int reciprocal, maybe, reciprocal, whatever. Reciprocal is equal to the sum minus the number. So if the target is 10 and we read a 7, then we search for a 3 in the set. So we say if vec, we should call it vec, unordered set, uset, I don't know, uset, uset. So if uset dot contains the reciprocal, then we see out found the reciprocal plus the number we just read. And then we insert it, and that's it. So we actually don't even need a second. What's 10, 8, 1, 5, 4, 7, 3, 9. Yep. And so you can see here that as we're going along, these guys are just getting inserted into the hash table. But once we typed in a 4, then it checks to see if there's a 6 in there already. It found it. Boom. There's your output. 7, no sum. But a 3, we found a sum now. 7 plus 3 is 10. 9, we got a 1 earlier. 1 plus 9 is 10. That's it. That's the whole program. So it takes longer to explain it than it does to write it. I think in my 12 o'clock class, even with an explanation, it was about 2 minutes, something like that, to write it. And typically on a job interview, they'll give you like 10 or 15 to write it. So, but this is a great example of, maybe not a great example, it's a simple example, let's put it that way, of dynamic programming, because we're writing down all the numbers we see. Because how most of you were trying to do it, if you were trying to do it at all, was you input all the numbers, and then you say for every number in the vector, search through the whole vector looking for the reciprocal. But you don't need to do that because you've already seen them once when you're doing the input. When you're doing the input, you just toss them into a hash table. And then if you want to ask, hey, have I ever seen this number before? It'd be like, yes, order 1 search and sort of order n search. And so it's much, much faster by using, bless you, girl, bless you. You're triply blessed. Quadruple blessed. Well done. So, yeah, hash tables. Who knew they were useful? All right, so that's called sum2. That's a fun little algorithm. Let's just say void sum2. We'll just toss all this into that. These are the kinds of things you need to, get practice at. There's a book called Cracking the Coding Interview, which I had. Oh, there it is. Why is Cracking the Coding Interview on your chair? Have you been reading this in your spare time without me? Do you have something to tell me about trees, graph theory? No? Chapter 8, recursion and dynamic programming. So there's an entire chapter on dynamic programming. It is a great tool, because anytime you can change the big O from exponential to linear or n squared to n, like that's just a massive speed up in performance. You know what I mean? Massive. It's called Cracking the Coding Interview. So if you like doing crack, wait. Dad. I'm not Rob Ford. Okay.
You cannot be saying these things. There are children in your
There's
house.
children in the room. My lord. My lord. If you guys didn't get the Rob Ford, he was the mayor of Toronto. This guy here. So he's like, yeah, I've done crack cocaine before. All right. It's cracked. All right. So yeah, it's called Cracking the Coding Interview, and it's kind of like the go-to book I recommend when you guys are like trying to get good, trying to get practice. Most people these days use a website called LeetCode. It's probably my number 2 site. I used to use HackerRank, but HackerRank charges you for the test cases. So if you pass everything, it's fine. But if you fail like test case 7, if you want to see what test case 7 is, they charge you money for it. And it's like, and sometimes it's not clear from the description. Like, all right, am I supposed to handle negative numbers? Am I, exactly what am I supposed to do? In the edge cases, they don't really explain it that well. And so, like, dealing with some of those HackerRank problems is annoying unless you pay the money to see what the actual test cases are. I like Code Wars. Code Wars, we have a group for Columbus Community College. And basically, they have... it's not really a war. It's not like a competition so much as... they've got different coding challenges, and they have a belt system. And so, like, as you advance through the belts, they get harder and harder, right? Does he sell crack? He just said, when he got drunk a few times, it's just one of those things that happens. What happened to Rob Ford? I don't know. That guy was an interesting character. Oh, is he dead? Oh, he died.
Who?
Rob Ford. He's the mayor of Toronto who did crack.
He died like
How did he die?
a long time ago, Dad.
He died a long time ago? 2016 was like last year, girl. What are you talking about?
That's before the pandemic. That is not just a year ago. I remember things, Dad.
Oh, he had cancer. Okay. So, 2016 it is when the timelines diverged. Death of Harambe sent our timeline spinning off into the darkest dimension. Toronto needs him now more than ever.
Why is Harambe a meme?
Why is Harambe a meme?
Yeah.
It was everybody said nobody's going to be, talking about Harambe in 2020. And, I don't know.
I feel like Harambe is just going to be one of those things that lives through generations.
Yeah, maybe. If it does, I'm not saying it's funny. Okay. So, LeetCode is kind of the go-to place. Like, people will talk about doing LeetCode problems to get ready for a coding interview. I think Code Wars is a little bit better, but, it's pretty standard to do LeetCode. All right. So, now we're going to give you another job interview question. This one is adapted from a friend of mine that worked at Google. And what we're going to give you is... Uncle Scott? No, Scott didn't work at Google. Scott worked at Microsoft. Scott's one, I think I talked about last time. He gives you a graph of the United States, and you have to walk from state to state on the graph, picking a letter from each state as you go along. And he asks, what's the longest word you can spell by traveling from state to state in America? And so that's actually a really interesting coding problem. And he asked people that at Microsoft for a decade every time they interviewed with him. Now, my friend at Google, 8 of the Jamba Juices here. My friend at Google did a variant of this. I'm kind of adapting it a little bit. So what we're going to do is maybe we'll just do a 2D array and just keep things simple. Int r of size, and size, maybe? Nah, we'll do a vector. We'll do it properly. Okay. So we're going to make a vector of vectors. C++, we're going to get it 2D arrays. All right, vector vectors and vec. And for int I equals 0, I is less than size, fs plus. Constant size equal to, we'll do a 4x4 to start, but we can increase that later. So for every row, we are going to create a vector of size 4. So vector dot push back a vector of integers of size 4. That. Oh, not size 4. Don't hard code it. Don't hard code it. Size. There we go. Okay. So we are making a 2D array, which is it's not exactly a 2D array. It's a vector of vectors. So every row is a vector. So every row could dynamically be a different size than the other ones. It's not great. MD array, I think. Is that out? C++ MD array. Is this ready for? Is this ready for the prime time? MD span, MD array. This proposal date. Is it accepted? Doesn't look like it. Is it accepted? No. Okay. Anyhow, yeah, the lack of a 2D array in C++ or 2D vector is kind of a gaping hole in the standard library. Bjarni in his textbook always uses creating a 2D matrix as an example of a class to build, and I don't know. We're not doing it properly. We're just doing a vector of vectors. Okay. Anyway. So we will fill this with data for auto reference row. So for every row in the vector, to y paste for. Let's not do that again. For every column in the row. So for every row in the vector, for every column in the row, we will vector dot at. No, we'll just say call equals read enter. Yeah, not good with prompt. It'll be a little spammy. Okay, so for every row, for every column, we're going to read from the keyboard a number. All right, and then we will do something similar to print it out. Cout call followed by a tab character, and then at the end of the row. Cout. Okay, so let's see if this works. Okay, 1, 2, 3, 4, 10, 20, 30, 40, negative 1, negative 1, negative 1, negative 1, 6, 4, 2, 9. Okay, looks like that works. Okay, so this will be the starter code I'll give you guys. And now let me explain the problem. This is again dynamic programming, and I'll even give you the conceptual solution to it. Okay, so that you don't just stare blankly at the screen again. Hopefully. All right. So what you do in this job interview assignment is you start in the top left corner of the map. So imagine this is like a chessboard. Ada, do you have a chessboard?
No.
Oh, okay. Imagine you're on a chessboard and there's like money on every spot on the chessboard.
The chessboard's literally just a graph with every other hole filled in.
Yeah, I mean, basically, we got a little grid here. We got a little gritty here. All right, so the top left corner has $1 on it. The row 0, column 1 has $2 on it. Like, let's say 2 gold coins. This one has 3 gold coins. This one has 4 gold coins. This one has 10 gold coins. So row 1, column 0. You guys understand? So there's different amounts of money on every square, and some of the squares have a penalty on them, or if you step on them, they take money away from you. And the question is, starting in the top left, going to the bottom right, you can only move east, you can only move down. So at every square, you got an opportunity, east or down, can't go out of bounds. What route can you take across this chessboard that will yield the maximum amount of money? You understand? Ada, what do you think? Which way would you travel across this chessboard? You can travel south, you can travel south, you can travel east. All of them have money except for the negatives. So which way would you?
Be positive.
Be positive? Be movie? What? Okay. So I think just eyeballing this, the maximum route would involve 1, then 10, then 20, then 30, then 40, then down. Okay. Now you might be inclined to say, well, let's just at every point look east, look south, and move in the direction that is optimal to us. Okay, but let me show you the problem with that. So let's do this again. 1, 10, 20, 30, negative 1,000, 0, 0, 0, negative 1,000, 0. I don't know. 1, 1, 1, 2, 2, 2, 2. Okay. Oh, shoot, I didn't line that up right. 1, 10, 30, negative 1,000. 1, 1, negative 1,000, 0. 2, 2, 2, 2, 3, 3, 3, 3, whatever the rest is for. So let's say you're starting here at the top left. And if every step you make is greedy, a greedy algorithm just looks at the local minima, the local maxima. So here in the top left, you can't just greedy algorithm it. Exactly. So you're like, oh, should I take $10? Should I take $1? Oh, I'll take $10. You go that way. And then you like $30 or $1. Oh, I'll take $30 and you go that way. And now you're stuck because both ways you go out of there are going to cost you $1,000. You're seeking that local maxima, and then you do not get a global maxima as a result. Well, in this required Dijkstra's algorithm, nope. It might remind you of Dijkstra's. It's not Dijkstra's, okay? Because Dijkstra's is trying to find the minimum distance. And what we're trying to do here is actually maximize the amount of money we pick up per square. So it's like the evil Dijkstra's. How about that? Where you're trying to get as big a score as you can.
Dijkstra's opposite edition.
Dijkstra's opposite edition. It's like kind of the mustache or whatever. I wonder did Dijkstra have a mustache? That his evil twin would not have one. His name was Edgar Dijkstra. Yeah, he's got a mustache,
right? And the mustache make him shave.
Yeah, so the evil version of Dijkstra would be clean shaven. Yeah, all these he's got. Yeah. I don't think that's Dijkstra.
Give him shady sunglasses.
That's not Dijkstra. Yeah, okay. That's evil Dijkstra right there. Okay. Okay. Oh, he got the Dijkstra prize. Okay, that makes sense. All right. Anyway, so what we need to do instead, how do we solve this? How do we? Remember we're talking about memoization, right? We've got a memo. We want to write things down. What could we write down? How can we? Looks like an older evil Matthew Lillard. You're assuming, bold of you to assume that Matthew Lillard's not evil already. So what could we write down as we go along through this algorithm? What could we write down so that we don't have to redo our computations? Because think about this. If we wanted to find the global maximum from the top left to the bottom right, we would have to try every possible route. But a lot of those computations we're going to be doing are going to be the same. We're going to be repeating a lot of those sub-computations. So what we can do conceptually is instead of trying to solve the entire problem at first, we use an existing solution to solve a problem one bigger. So let's take the smallest solution possible in this, which is, it's size 4. But imagine this is the entire grid, right? It's just one number. It's 1 by 1. How hard is it to find the global optimal from this? If you've got a single square on your chessboard, it's got $10 on it, how hard is it to find the maximum value from the top left to the bottom right? Answers on chat, please. Yeah, you're already there. You've already solved it. $10. Okay, cool. That wasn't hard, right? One operation. Yeah, all right. We're done. Now, imagine that you write this down. Okay, let me maybe plug in my tablet here. This will be easier than doing it in text. But imagine as you're going along, you write down the global maximum to that spot. Okay, so instead of dynamic programming. All right, so let's draw it out here. So this is our best, most optimal table. Okay, and so this is going to hold all of the solutions. In other words, the highest amount of money we could possibly get to that point. So let me go slap this over to the right-hand side of the screen, get my face out of the way. Can I minimize the left-hand side here? There we go. All right. So I'll put my face in the middle. There we go. All right. So here's our sample data over here. What is the what is the maximum amount of money going to this square right here that we can get? If that was the ending spot, what is the most amount of money that we could pick up on the table? $1. Good. And then we're just going to go left to right. Okay? And we're going to solve this whole thing left to right using, this is a memo. Okay? So what about this square? So we know the maximum amount of money if we're coming in from the left, and we can't come from the top, right? So what is the maximum amount of money we could get on this square if that was the ending zone? Like if that was the ending zone and we ask, what is the maximum amount of dollars you can pick up on the table? It'd be 11, right? Cool. It's not too bad. What about here? If that was the ending zone. You see what we're doing? We're solving it for each square along the way, and we're using the results of the prior computations to solve the next bigger iteration of it. So here, we can look at the prior computation, which is 11. So there's $11 possible coming from row 0, column 1. And on this square, there's $30. And so 30 plus 11 is 41. Right? And so what about here, if that was the ending zone? Calculator time. $959. All right, cool. All right. Negative 959. Not positive. Okay. All right, Gunnar. What if this was the end zone? Now we've already solved it above us, right? So there's a dollar. There's a dollar on the board here. If that was the end zone, what was the max amount of money we could have picked up? If that was the final destination, like the movie. Not here. No, because we're not coming from here, right? That doesn't connect. This is the starting zone here. That's the start. All we could do is start there, travel south, and finish. We're done. Nope, not one. Not one. The answer is 2. Because we could start in the top left corner that has $1, and we could move south, which has $1. And if that was the ending zone, the maximum money we could possibly ever super duper pick up was $2. Now, Gunnar, I'll let you rehabilitate yourself. Let's say this is now we're coming to a place where there's a decision to be made. So we know that no matter what route we take, if we're coming in from the north, there's $11 that way, and if we're coming in from the west, there's $2 that way. So which way should we come from to come to this square and pick up $1? What do you guys think? Should we come in from the north? So should we come this way, in from the north? Or should we come in from the west? And we don't need to look at every possible route to get there. We have solved the biggest, most optimal possible number that we could get to if we were there was $11. Now there's only one possible route, but just the same. Trick question: diagonal. No, diagonals are not allowed. Only east and south. Yep. So what do you think, Lamar? Should we come in from the north? If this was our ending spot, row 1, column 1, should we come in from the north this way, or should we come in from the west this way? If we want to maximize the amount of money that we are picking up on our chessboard here. There's one gold piece here. There's one gold piece there. So we're going to pick up one. Okay. You'd say the west? No. Why would you say the west? There's $2 that way. We would only have $3. We want maximum money. We want to come in from the north. $12. Yep. So the most money we could possibly get if row 1, column 1 was the destination was 12. And that would be coming in from the north, right? We would start here, move east, pick up 10, move south, pick up 1, right? Now we have solved it for row 1, column 1. And now we can use that for row 1, column 2. So here, if this was the ending spot, now there's negative $1,000 on this one, so it's a terrible spot, but we still need to find out what is the maximum amount of money we could get if this was the end. Preferred, what do you think? Negative 959, exactly. I pride myself on not opening the calculator up again. We got it written down. Look, it's a memo. I've already computed that one. Okay. Because but for this one, we actually had to look at 2. We could either come in this way or come in that way. All right. And we want to have more money, so we come in from the route that would make us more money. Now here, there's $0 on the table, and both options are the same, so it doesn't matter, right? It doesn't matter which one we pick. So we'll just say this one is negative 959 as well. Do you guys understand? So for this guy here, if that was the ending spot that we had to move to, the best we could do is negative $959. That's the most money we could walk away from with the table, and that'd be going along the top row to the 30, and then either south or east to the negative 1,000. They're both the same. Doesn't matter. Okay, so starter early. You're up next. What if this was our end zone? There's only one route we can use to get here, right, Stevie? There's only one route, because we always start here. We always start in the top left. And if this was our finish line, there's only one possible route that we can take to get there. Because we can only move east and south, and if we move east, we can't get there, right? So, Stevie, what is the maximum amount of money we could get if that was the finish line? Say 3? You're just counting 1, 2, 3. There's $2 on the table there, right? So there's $1 in the starting square. There's $1 south, and then there's $2 on that square. Okay. So the answer is 4. Now, Orozco, you can do this computation. What is the max amount of money we could get if that was the ending zone? You have 2 options, either 4 plus 2 or 12 plus 2. Which one's bigger? Angel. 12 plus 2, yeah. And so the most money we can get from here is 14. Then from here, 14 is bigger than negative 1,000, so we'll 16, 18, going south, 7, 17, 20, I guess, actually. 20 and 23. That is the answer. 20, that's a terrible 2. 23. So if this was our input here, your code, your program should output 23. Okay. So there's a couple special cases you have to watch out for. Top left corner, you don't look at any of the previous people. That's the starting point. Just the value is whatever value is on the table there. If you're on the top row, you don't look up. If you're on the left column, you don't look left. Other than that, every square, you're looking at the person to your left. You're looking at the person above you, and then taking the value that is bigger and adding the amount of money on that square to whichever one is bigger. And then that is the optimal solution to that point. And then as you grow through the array, as you pass through the array, you're constantly to be using the pre-computed solutions to the smaller problem to solve the next bigger problem. And thus, this whole thing here can actually be done at the time that you read the array. It's an order n algorithm. Okay? And that's basically as good as you can get, because at some point you just got to read all the data, right? You got to load it from disk. That's an order n operation. So You can't do any faster than this. This is pretty fast. You can actually do it as you're loading. Because as you can see, you just go left to right like that. As you're just loading the data, you can just update this best, most optimal table, the memo. And then when you finish at the end, the last value is the answer. And that is the Google, or a Google, I should say, job interview problem. All right, so go ahead and start streaming now. And let's see you guys try to implement that algorithm. It'll take me a while to figure out the code for it. We'll just, get cracking.
2 wandering traders just spawned inside my underwater, like.
2 wandering traders underwater? They are wandering then. All right, so start streaming. Begin. Okay, so a lot of more blank looks, so let's just do this. So we've got, some people are trying to do it using the range-based for loop method. Not going to work, because it's a case where you actually need to look at the people, the index to the left or above you. So there's a couple different special cases we need to look at here. First is top left corner. Oh, it's a README file. Read-only file. It's main.cc. So the top left corner is when I is equal to 0 and j is equal to 0. Olson, I think, changed mine from not I to I double equals 0. It's, this is not allowed in Java and some other languages. You can't not a integer in other languages. But in C++, it's fine. So we're saying if I is 0 and j is 0, do nothing. Why? Because the array at, or we're calling it vec, but whatever. The vector at 0, 0 already has the optimal value. Right? The top left corner, if that was the ending zone, the answer would be the value there. Right? You start there, you pick up the 10 coins or whatever, and you leave. You're done. If that was the place where you end, the value on it already is the optimal value. And like I said, I'm not actually going to be creating a second 2D array. I'm actually going to be just rewriting the input array, which, is fine as long as you don't need the original values anymore. Next special case you have to handle is if you are on the top row. So the top row, you just add the values from the left, right? So, like if we go back to here, the these top row values were you just add all of them up in order because they can only come from the left. So we are going to say vector dot at I, which is 0, dot at j is equal to vector dot at I, which is 0, dot at j minus 1 plus vector dot at I dot at j. So what we're doing here is remember how we're picking up coins from our current spot? We're using the maximum value from the left spot and adding the value at our current spot, and that is the maximal value at our spot. And we're just there's no intelligence or anything like that here. It's just you just add up all the people in the column together. It's probably gonna get mad at us for it's fine. Sign conversion, whatever. Lord. I'll just do this. Turn off all those warnings. There, no more warnings. Now you have to be very cautious when you're doing subtraction with an unsigned integer. That's why in general I tend to prefer using integers. A size t, if you subtract 1 from it, when it's 0, it underflows and goes up to maximum integer, maximum 64-bit integer. So this is safe though because we know that j cannot be 0. If j was 0, we would have continued. So we're going to be in bounds, probably. All right, and then we have another special case for the left column. And so the maximum value you can get at the left column. Let me just make this a plus equals really. Copy and paste that. It's just the value of the guy above us plus our value. So remember when we were going down, we just add all the values up, because the optimal way of getting down to the bottom left corner is just by going south, 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 south. So we just pick up all the coins along the way. All right. And then that's that. Now we're coming to the heart of the problem. The heart of the problem is the intelligence, right? And so we have to look at, and we can probably do an else here and an else here, and then an else go block here. And so now we need to determine if we should come from the north or from the west, right? So Gunnar was like, let's come from the west. They've got less money, but we're trying to get more money, right? And so coming from the north is the correct approach. So coming from the north, we would have picked up $11. Coming from the west, we would have picked up $2. So we come from the north, and we've got $1 on our current square on the chessboard. So pick up that $1 and the 11 along the way. And so the max we can get to here is 12. So we have to look at north and we have to look at west. So we have to look at the two and see which one's bigger. So integer max is equal to let's not call it max. X is equal to the max of the person left of us and the person north of us. Here's the person left of us. Did that not select? Person left of us, and go away, Commander Conquer, and the person north of us. And so we're just going to add that to the value at our current tile. And so we can actually just copy and paste this. In that case, we're going to need curly boys, and that's fine, and that's fine, everything's fine. And that's it. That's the entire algorithm. Yep. And so when we get to the bottom right corner, the value there is going to be the max. So cout max value picked up at vector.at vector.size minus 1. I'll just do size minus 1. At then 20, 30, 40, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Max value picked up is 100 as it went to the right and then went downwards. Okay. 10, 0, 0, 0, 20, 30, 0, 0, 0, 0, 40, 0, 0, 0, 0, 0. Max value picked up is still 100 as it goes south, south, east, south, so on and so forth. So there you go. So that is a classic dynamic programming job interview problem. And if we make it more complicated, 7, 4, 3, 2, 10, 1, negative 9, 6, 10, 0, 1, 3, 9, 4, 3, 10, I don't know. Then it will figure out the optimal way without having to try every single possible route. Because by the time you got to the end, there's only two things you need to worry about. Should I come to the end from the north, or should I come to the end from the west? And whichever one's bigger, you pick that one. And so you just add the current value to it and repeat. And so by using a smaller subproblem that you solve, you can kind of grow the solution through the array until the entire array has been solved. And if I in fact printed out the array at the end there, you will see it has been solved not just for the final point, but for every point. Okay. So let's do 1, 4, 3, 9, 12, 1, -2, 6, 1, 11, 4, 5, -9, -9, 10, 3. And so you can see here, it has printed out, that's the input there, right? So the maximum amount it could be here is 17 because our input was 1, 4, 3, 9, right? So 1 plus 4 plus 3 plus 9 is 8, 17. And so we've solved the maximum amount we could get at every square. And then heading south from 17, it's 23 because that's bigger than 12. Then heading south from there, the biggest value is 29 plus 5 is 34. Heading south from there, 39 plus 3 is 42. So we have solved, that's the solution for every square. That is the most coins we can pick up in every square. And that is our class for today, people. So that's all order in. Yeah, you can see this. We don't do any searching at all. In fact, we could be doing this as we read the array. So you read a number in, and then you update it. And you read a number in, you update it. I just split it off into a separate for loop so you can see the solution here. But yeah, it's proportional to the number of elements in the array. So if there's 100 elements in the array, we'll do 100 operations. Yeah, it doesn't have to search every possible route because I've written down on my memo pad the fastest way to get to every spot, and so I only have to look at 2 spots instead of all the spots to figure out what's the best way of getting to me. It is very cool, and that is a Google job interview problem, and you can see that at the end of the day, while 2/3 of the class is just kind of staring blankly at their screen, not typing anything. At the end of the day, like, this is not actually super bad, right? Like, you have to be careful of your edge cases. You have to be careful not to go out of bounds. That's that -1 there could cause a crash. The -1 here could cause a crash because if you're not careful bounds checking, and you're on the left edge, you say, "Hey, who's to the left of me?" You segfault or throw an exception. If you're on the top row, "Hey, who's north of me?" Segfault or throw an exception. Whatever. So there's a little bit of spiciness involving subtracting 1 from an unsigned integer that makes me feel very nervous. That's why I used integers to begin with. But we have prevented I and j from being 0 because we check for that there. If they're both 0, we continue. If one's 0, then we subtract 1 from the other one, and so it's safe. But this pattern here, you might want to admire, screenshot, peruse it later, summer, print it out, have it up on your wall, frame it. Because this is a pattern you'll see a lot when you're working with 2D arrays. Like that pattern there, very common for 2D arrays, 2D vectors technically, to not go out of bounds. And if you're reading from the right, then you have to make sure you're 1 in from the right-hand side. If you're reading from the guy below you, you have to make sure you're not on the bottom row. So I'm only bounds checking on 2 of the sides. Normally you bounce check on 4 of the sides, but we can only get values from west and north. So yeah, that's all that's necessary. Put on your fridge, exactly. So that's it for today, guys. Thanks for coming out. There'll be a quiz on dynamic programming, and then there will be one last class on Friday, and we'll go over the final and stuff then. And then we'll be ready for the final. And have a great day. Peace out.